Yes, hello everybody. Thank you very much. Thanks a lot to the organizers for bringing together this kind of nice conference. I enjoy it really a lot of nice discussions, and of course for giving me a space here to speak about my work, which will be about monitored free fermions, or free in parentheses. So what is a monitored fermion, you might ask, or you might not. So the idea is that we say, well, of course, we have measurements. We deal with measurements all the time when we talk about quantum physics, but mainly because we want to detect something. We want to get information on our system. But we can also do measurements to evolve the state, right? So if we do a measurement on, let's say, measuring a particle density somewhere in our system, we get an answer. And after we got this answer, our system collapses onto the state that is compatible with that answer. And so there's an evolution induced by this measurement. And then people started to wonder, not long ago, starting 2018 essentially, so what happens if we kind of have a competition between this projection coming from measurements and unitary evolution? And we wanted to understand this too, because these papers got cited a lot. And we thought, well, we want to do that too. And we thought, let's start to understand this analytically by looking at the simplest model where we have this competition. And 3 years later, I'm still talking about this stuff. So either there's a lot to say about this, or we are not particularly smart. So let's see what you think about that. Okay, let's get started. Little reminder about kind of entanglement, measurement, Hamiltonian evolution. When we think about a system, typically when we make a measurement, we think of reducing kind of correlations or entanglement in the system. The simplest scenario is this: we take two spins, we put them in a Bell state, now we measure the orientation of a single spin. No matter what the outcome of this measurement is, the system is in a product state, so the two spins are no longer entangled. Simple scenario. Now let's make it a little bit more general and say, okay, what do we get when we have a system that is kind of composed of many particles, and we can compose the system into like subsystem and rest, and we have a Hamiltonian evolution. Typically this Hamiltonian exchanges particles, correlations, magnetization, I don't know. It kind of exchanges information between the subsystem and the rest of the system, and that generates entanglement. Now if I measure something in the subsystem, I know I get information onto the subsystem, and obviously this information can no longer be shared with the rest, because I know this piece of information, some qubit or whatever, is in the subsystem. So naively I can imagine, well, this measurement of the subsystem has reduced the entanglement of the subsystem with the rest, because this piece of information is no longer shared with the rest of the system. And so this naturally gives this competition between a delocalization of information and the localization of information due to measurement. And information can be very broad here. Maybe there's a particle that is delocalized between two subsystems. That's information that's shared between the two systems, a qubit, or something more complicated. Okay. And so what we want to look at is a scenario where we have a wave function, a quantum many-body system, that evolves with some Hamiltonian. This Hamiltonian builds up entanglement in the system between subsystems. And then we do measurements, for instance, of particle number, magnetization, as I said. This reduces the entanglement between the subsystem and the rest of the system. And this competition is something we want to understand. So do we get a boring state? Do we get an interesting state? What happens? So that's the kind of setup we have in mind. It's a kind of sketch picture where we say, let's take a 1D system, maybe a chain of spins, or maybe a lattice where we have fermions. So we will talk about the fermions, and do some evolution with some Hamiltonian up to some time, which entangles these different sites or these different spins, and then do measurements, which kind of disentangle these fermions or these sites or these spins. And the way we're doing this is by applying this generalized projector over here. So that's kind of maybe something you're not so familiar with. I will come back to this in a second. So, but for now, have the picture. We do some time evolution with a Hamiltonian, then we do a measurement, then we do time evolution with a Hamiltonian again. So if we measure operators, O, that do not commute with the Hamiltonian, then this system kind of does not come to a rest, right? Because I don't have a shared eigenbasis of the Hamiltonian on these operators. Every projection goes into a state that is not an eigenstate of the Hamiltonian. The system evolves. I can measure again. And so I have a competition in the dynamics of the system that is kind of similar to the competition that I have when I talk about quantum phase transitions in the ground state. So here I have a Hamiltonian in the ground state that is composed of two different pieces. If they don't commute, then I can tune between the ground state of one to the ground state of the other, and in between there is a quantum phase transition. And we hope to see something here, but now in the dynamics. Okay, so a little word about this generalized projector. Any operator we can write in a spectral decomposition where we have the projection onto the eigenvalues, onto the eigenstate, and these eigenvalues over here. Now, and so if I kind of do this spectral decomposition for this projector over here, I get this form. So I just have the eigenvalues over here, and the projector now acts linearly, and I have two different limits. And one limit is the weak measurement limit, where this gamma dt, this prefactor over here, is much smaller than the level spacing. So this is a weak measurement. I get information onto the state, or about the state, but I don't know in which state or what is the eigenvalue. So I'm not projecting onto an outcome. I just make one outcome more likely. You kind of have seen this in quantum mechanics 1. That is kind of a Stern-Gerlach experiment. I say what I do is I measure the position of a particle, and from that I infer whether it has a spin up or a spin down. If I wait for a long time, then I get a bimodal distribution. I say, okay, this has spin up, this has spin down. But if I kind of look at the particle very shortly after I kind of switched on a magnetic field, I just get a trend. And that's what's happening. So we can interpolate between a weak measurement where I don't learn much about the state, or a strong measurement where I learn in which eigenstate the system is by kind of tuning this parameter gamma dt over here. And we will work in the kind of weak measurement limit where we're doing this, where it means we have to wait for a long time in order to get enough information to know whether the system is in an eigenstate A or eigenstate B. Okay. Kai already mentioned this. Now what happens is we're evolving individual wave functions. So we prepare a state, we evolve it over time, we have Hamiltonian, we have measurements. Finally, we arrive at some quantum state at the end. This is a nice quantum state. It's well defined, but it's random because I cannot predict what the outcomes of measurements are. I cannot do this in advance. And so this state depends on the outcomes of all these measurements. And if I do the measurements again, I will get different outcomes and I will end up in a different state. So I get an ensemble of random states, and if I just naively average over all the states, it's a totally mixed ensemble. So there's no information in this ensemble. So if I ask about kind of random correlation or just kind of linear correlations like magnetization or density-density correlations in these ensembles, they're like boring. They're not interesting. But individual wave functions are still interesting. And the way to kind of extract interesting here is to look at the entanglement entropy. I don't have enough time to explain why this is the case. That's not magical. That has a very nice physical reason, which we can maybe discuss afterwards if you're interested. But entanglement is the property that we're interested in. And so now what does entanglement do if I'm just having unitary evolution and I start with a random state? Then a random state has a lot of energy, and after I do the unitary evolution for some time, it will end up somewhere in the middle of the spectrum. I have a superposition of many eigenstates with random phases in the middle of the spectrum, and that gives me a volume law entangled state, typically. That's very generic. However, if I measure a lot, if I measure constantly, then what will happen is I know exactly what I have. I have like a product state, which is the eigenstate of all the operators that are measured, and that has an area law entanglement. And so if I measure a lot, I have area law. If I not measure at all, I have a volume law entangled state. So somewhere in between, something has to happen. And what happens actually is there is a phase transition. And this phase transition, there's a critical point where this competition kind of really imprints very long-range correlated quantum states. And that has been found essentially first in these circuit models, like Clifford circuits. We had this before. We don't need to know what a Clifford circuit is, just this kind of picture. You have unitary gates and measurements. So I said we want to go to a very simple scenario where this competition takes place. So let's do that. Very simple. Free fermions hopping on a chain, and I measure the particle density at each site in the system. What kind of competition do I have here? I have a Hamiltonian that introduces hopping of particles. So particles are delocalized. Entanglement is built up by this. Now, when I ask of a subsystem how many particles are in there, I have uncertainty because the particles are delocalized. This uncertainty is directly transferred into entanglement. If I measure a particle, I know it's there or not, so it cannot be entangled with the rest of the system. So that's the competition, localizing particles by measurement and delocalizing them by a Hamiltonian evolution. Let's look at the entanglement entropy and what we find if we do that. So this is a Gaussian evolution. We can simulate this very easily, going up to system sizes of 1,000, 1,000, 2,000, 5,000 particles, no problem. Let's do that. We find if the measurements are rare or weak, there's an interesting behavior of the entanglement entropy that it grows logarithmically with the system size. And this was very fascinating for us because we thought, well, that's not generic. That's something we see typically only at a quantum critical point, that entanglement entropy grows logarithmically with the system size. So okay, that's nice. So there's an extended critical phase in our system. If we increase the measurement rate, then the entanglement entropy saturates and we get an area law. So like a product state. This looks really nice. In between, there's a phase transition. And this scenario kind of is very familiar to what we know from BKT type transitions. So what means BKT is that we have a critical phase, an extended critical phase, and we have some tuning parameter. And when we tune this parameter, the system actually acquires a scale. So this is not generic, that you have a scale invariant region and you tune some parameter and then a scale emerges. The only scenario that I know or that I knew where this would happen is in a BKT phase transition. So looks very familiar to that. Well, can we kind of nail this down? Yes, we can. We looked at the prefactor of the entanglement entropy and looked what its scaling is, and it matches very nicely this kind of finite size scaling form, which is the right scaling for a BKT transition. And what's the funny thing about a BKT transition? It's a phase transition of infinite order, not first, not second. And this is manifest in a correlation length that diverges exponentially when we approach the critical point. So not like a power law, but actually it has an exponential divergence, and that's the factor in the exponent over here. And gamma is the measurement strength. So that's consistent. That made us even more happy. Then we looked at this weak measurement phase. So this region over here where we have a logarithmic growth of the entanglement entropy. And we were asking, okay, we are in 1 plus 1D, and we see something that looks like a critical phase because it has this entanglement scaling. Does it actually have conformal invariance? Because usually in 1 plus 1D, if you have a critical point, that also has conformal invariance. That means it has a very strong symmetry in the problem. And one way to check this is by looking at the mutual information between two subsystems A and B and plotting this as a function of these endpoints here, which can be, in terms of this ratio here, which are differences of these endpoints, which is a self-conformal invariant. And when we do that, we see some scaling collapse indicating, well, it looks like there's some emergent conformal invariance in this system. And that's funny, because what did we do? We just have this Hamiltonian of fermions hopping around, and we measure the particle number, and we prepare somehow a very exotic, interesting state, a conformally invariant state of fermions. That really made us we were super happy. We published this. Some people loved it, some didn't. Just the question.
What's the most natural way to realize that weak measurement physically, if you had to choose an apparatus to make that happen?
Okay, so one comment is it does not so much rely on whether weak or strong measurement, so both cases work. Weak measurement, you could say, I don't know, maybe you want to realize your free fermions by some XY model that you can realize in Rydberg systems, and now you couple every spin in the XY model to an ancilla, and you measure this ancilla.
Okay,
so it's kind of doable. No? Okay, not everyone was happy, so this is still a kind of ongoing discussion, which makes this very interesting. That's why we're still working on this. So is there now a transition or not? So the first paper were actually not ours. It was by Andrea De Luca and his collaborators, where they were looking for this volume law that I mentioned you should expect when you just have Hamiltonian dynamics. And they said there is no volume law, and from that they concluded there must be just an area law. So they kind of even did not look for this critical phase. Then there were our papers. We also have some analytical works on this, which I will present in a second, which said, yes, there is a transition. Then a little bit later, no, it's not. Then again, yes. And then this spring, this paper came out, which is a great paper. We said, no, it's not. Because actually, how we should see this is it's 1 plus 1D quantum dynamics. Let's compare this with 2D disordered systems. And 2D disordered systems, that's kind of an ongoing story still, although people look at this since the 50s. And what happens in 2D disordered systems is we know if we are in 1D, we always have localization if we have disorder. There's no Anderson localization, it's always localized. In 3D, we have a transition from a metal to a localized state as a function of the disorder strength. That's Anderson. But in 2D, that's anyway the magical dimension for anything. In 2D, you have a phenomenon that's called weak localization, which means if you go to astronomic large scales, you're always localized when you have disorder. But at short enough length scales, the system looks metallic. And so that is kind of the signature, would be the signature of a metal, this logarithmic entanglement growth. A 2D metal realized in a 1 plus 1D circuit. And this would then indicate that actually the system is always localized. But the localization length, just as for BKT, diverges exponentially with the disorder strength. So it has the same form as here, just this gamma c, the critical point, is not at a finite value, it's at 0. And this is kind of notoriously difficult to detect. Yeah, there are still people, disorder, think, I mean, free fermions with disorder, what's not solved about it? A lot. But there are signatures that one can track. Namely, there's the phenomenon, as I said, this weak localization. This should show up as kind of logarithmic corrections to your conductance. That's what people see when they search for, when they look for weak localization in 2D metals. How would this enter here? Here, this would enter as a correction. So we have a logarithmically growing entanglement entropy over here. The weak localization scenario would say it has to saturate at some point, but our system sizes are not large enough to see this. But what we should see at short system sizes is a correction that's minus log square, log L square. So that's weaker for small system sizes, but eventually wins. But we don't see that correction. We do numerics for very large system sizes. We don't see that. Okay, so kind of we were wondering, how does the story continue? We're still working on this. And if we kind of follow this periodic behavior over here, you will know what the answer is, at least the answer for the next paper. Yeah, so we have a little bit more on this, where we actually make statements that there is a transition. But let's look into the analytics, because that's really interesting, my opinion. So we look at observables now that have to be nonlinear in the state. We said if we have this linear stuff and we average over all the measurement outcomes, then the answer is boring. The simplest thing is actually something like this nonlinear density-density correlation function. It's nonlinear because we're averaging over this, which is like a fourth power in the state. So it's or a second power in the density matrix. And that is actually enough for free fermions to compute the entanglement entropy if you know all these correlation functions. So you can infer the correlation functions, the entanglement entropy from particle number correlations in free fermion systems. So what do you have to do in order to compute something like this? You have to go back to disordered systems and use their tools and say we have to introduce replicas in Hilbert space, so many copies of the same state. So we get the same state if we pretend that we do measurements with always having the same outcome. So we introduce this replicated density matrix, which is a tensor product of many identical states that all have experienced the same measurement outcome. And then we're measuring over the measurement, then we average over the measurement results. So what happens is we write down this replicated density matrix, which is the product over all these evolved density matrices normalized by their trace, because after each measurement, we have to normalize the wave function, right? And then we take the statistical average, where we kind of now average all these replicated density matrices with the distribution for measurement outcomes. And that gives us this expression over here. It looks innocent, but and it's very close to what people from disorder problems would get, but there is a difference. If I think about disorder, the disorder that I get, disorder realizations in systems are independent of my state, right? So I just say, well, I have some disorder realization in the material, and I ask about the quantum state that is an eigenstate of the Hamiltonian or the ground state. But here we do dynamics and we do measurements, and a measurement outcome is not independent of the state. It depends on the state. That's Born's rule. Measuring 1 or 0 depends on my quantum state. So this translates in this disorder problem into disorder that's correlated with the actual quantum state. And so we're not back to just a disorder problem. It's a different scenario. Good. So what do? I want to speed this a little bit up. We derive this replica density matrix, do this averaging. That's not easy because that's a fraction. So here now the replica trick comes. You compute this for a term that's not a fraction by introducing, instead of using 1 over here, we use n and say n is larger than r. So that's a linear quantity in the state. We can compute this and then later take a limit of sending n to 1. Disorder guys would send n to 0. That's the difference. Okay, we can write down the evolution equation for this, and we see there's some dephasing part now in replica space that's not interesting, but we see this non-Hermitian evolution over here, which tries to minimize fluctuations of this operator that we measure in replica space. And now this sounds a little bit strange. If you're not familiar to it, let's have a picture for this. For the fermions, we have the same expression over here. And now we imagine, instead of just having fermions on each lattice side, we have n flavors of fermions on each lattice side. And these measurements want to align these fermions like a big spin and make always kind of either n measurements, now I call this m fermions per side or 0. So it's like a big spin that's rotating in replica space. The Hamiltonian doesn't care where this spin is located, but it couples different spins, and the measurements want to align these spins. And that's a story that is very kind of appealing for deriving a nonlinear sigma model from this. So we take our fermion theory, we write it in terms of a matrix theory, and then we parameterize it in terms of the relevant degrees of freedom, which are rotations of this big spin in replica space now. So that's the stuff that's going on. This gives you always the same theory. It always looks like this, where U is a unitary matrix. And you wonder, okay, if it always looks like this, what's the catch? Are all systems identical? No, the question is, what is U? So U is the matrix that parameterizes the rotations that are allowed by symmetry. And now the tricky part starts. So what we did is we said, well, we have fermions in 1D. That's essentially Dirac fermions. In 1D, there are emergent kind of left movers and right movers. Particles are either traveling to the left or to the right, but they're not undergoing diffusion. And so the right theory is kind of a Dirac theory, and this gives you exactly the phase transition we saw in the numerics, or we believe we saw in the numerics. However, you can write down general nonlinear sigma models and do RG. And what you find is then again, 2D is the marginal kind of dimension for this, and everything depends on, so the canonical scaling behavior does not change the flow, and it depends on the beta function, and this beta function highly depends on symmetry. And now we have kind of different scenarios where we say, well, if we assume that we have 1 plus 1D is the same as 2D and diffusion, we have weak localization. There's no phase transition. If we say we actually have emergent Dirac fermions in 2D, then we have actually an S U2M model. There's an S missing over here. This has a phase transition with localization. If we assume something else, like Majorana fermions that we're measuring, we have an SO2M model, and we get weak anti-localization. And weak anti-localization is what Kai talked about. It gives you this, this Goldstone phase. So that's kind of the disorder analog to the Goldstone phase. So everything depends on symmetry now, but no one knows what's the effective symmetry here. You can only confirm this with numerics. So we can go back to the slide I showed before and interpret our data, maybe for 20,000 sites or so. Okay, but what this teaches us is kind of free fermions in 1 plus 1D quantum circuits with monitoring are very interesting, and they have some relation to kind of 2D fermions with this order, which is a kind of, as I said, very interesting scenario. You have kind of a lot of review articles. We find all kind of interesting phenomena, but it's not the same because we have this different replica limit where we say everything, our disorder potential now depends on the state because we're doing measurements. And kind of the only person who knows what this means is Wegener, but he's not active anymore. So the question is open to the public, I would say. Thank you very much.